calculating the pH of a strong acid is pretty straightforward. If by chance this were a 1 molar solution of hydrochloric acid, we know that it dissociates 100%. That would give us 1 mole of hydrogen per liter, and we could just take the opposite log right away. The problem with a weak acid is that just because this is a 1 molar solution doesn't mean that I get 1 mole of hydrogen per liter. And in order to do pH, I need the concentration of the hydrogen ion. So we'll usually be given a K value, the acid dissociation constant, and they're often small for weak acids. We're going to use that to figure out how far forward does this go? How much does this hydrofluoric acid dissociate? If I could figure out then the amount of hydrogen, I can go opposite log. So again, they kind of break this down step by step. The major species in the solution, this time it's neutral HF molecules and water. Last time we dissociated the hydrochloric acid because it was a strong acid. But this time with a weak acid, those particles are primarily neutral molecules. We do not dissociate by much. So the major species are really just the 2 neutral molecules. The dominant source of hydrogen then, let's compare K values, dissociation constants. For the acid, our Ka is 7.2 times 10 to the negative 4. However, Kw, the dissociation constant for water, is like 1.0 times 10 to the negative 14. Okay, so between the two, I have a feeling we would have got this right. The dominant source of hydrogen is still the weak acid. This guy's the winner. Is there a little bit of hydrogen coming from the water? Sure. But in the end, it'll be pretty insignificant. It's not going to change our pH calculation. Okay, so they want us to write an equilibrium expression for the dominant equilibrium, which we should probably kind of write an equation. There's probably 2 ways that you could write this. The most common way you'll see a weak acid, hydrofluoric, they'll probably put water in there as a reactant. It just kind of gives you a better snapshot of the hydrogen transfer. The weak acid will donate the hydrogen to the water. And so on the product side, we'll be left with fluorine ions and the hydronium ion, H3O+. It's a little bit more accurate too, because if you really do have positive hydrogen ions swimming around in the water, they are attracted to the negative oxygen end on the water molecule. The equilibrium expression then would look kind of like this. Ka equals products, fluorine to the first, hydronium to the first, all over. Okay, do we include the water? Hopefully you said no. We're not going to include water because it's a pure liquid. The rest of these guys are in solution. We would label all of these as aqueous, but we're not going to include the water. No pure liquids or solids. So this will really just be all over HF to the first. Okay, so we need to set up an ice table and somehow solve for, in this case, we'll write it as H3O, the hydronium ion concentration. If we could solve for that guy, then we can just opposite log and boom, we got the pH. So let's do an ice table. Often if people have any ice table issues in chapter 13, they become resolved in chapter 14. Because you just end up setting up so many ice tables. Fluorine and hydronium. You'll be able to do these forwards, backwards, upside down in your sleep. These are great. We're going to ICE. Ice table this. The original amount of HF, the concentration was 1 molar. And technically we're not going to include the water, so we'll just kind of scratch water. These products are 0. I know they can't be 0 at equilibrium, so we have to shift forward. We'll call it x. We'll bring this down by x. I don't care about the water. These guys are going up by x. So at equilibrium, this is really just 1 minus x. Scratch, I don't care. And x and x. Okay, so we know K. Ka is 7.2 times 10 to the negative 4th. That should be products, x to the first, over reactants, 1 minus x. Okay, that's not bad. Now, I could kind of simplify this a little bit. On the top, that's going to end up being, what, x squared? And I could cross multiply it. However, I'd probably be left with the quadratic equation, right? We don't really want to do that. So what if we try the 5% rule? That K value is really small, so whatever x is, it's also really small. So let's try getting rid of it. Let's try it. Because boy, does this make your math a lot easier. If I cross multiply, I'm just multiplying by 1 equals x squared. So we could just take the square root and the square root, and bingo. X equals square root 7.2 times 10 to the negative 4th. The original molarity had 3 figures. Let's say 0.0268. Okay, now should we check the 5% rule? I suppose we could check. We made a little assumption. We assumed that HF on the bottom was really just 1 molar. When I did my math, I just used it as 1. If I calculate it, I'll take 1 minus x, which is what, like 0.973. Okay, now I think that some of us just by inspection can say, oh yeah, those don't differ by 5%. And if I plug it in my calculator, we would be right. They differ by about like 2.7%. The 5% rule was valid. So we'll just say 5% rule, check. I honestly don't always check it. I usually don't check it. I think about it, like I make sure that my x does come out to be something relatively small. And I kind of think about like subbing it in, but I don't always calculate the exact percent difference. Think about it this way too. You do not need to solve the quadratic equation on the AP test. So the 5% rule is always going to work. We'll say we checked it, but I honestly don't. You would not need to use the quadratic equation on the AP test. The 5% rule is 1,000,000% acceptable. Okay, so now here's what we can do. X is the hydronium concentration. We can do pH right away now. pH is opposite log of 0.0268 molar hydronium. Oh, okay, cool. So it's like an ice table, but really all we're interested in getting out of it is the concentration of hydrogen, or hydronium. How far forward does this go? We plug it in, and we get a pH of about 1.57. Done. See, this really isn't bad. It's just another application of these ice tables and K values. Solve it for X. X will usually end up being your hydrogen or hydronium concentration. Boom, opposite log, you got the pH.